All right, now we're going to get to some waves proper instead of just talking about simple harmonic motion. So this will be a short little video about wave fundamentals. Waves here. So just a brief introduction. Um, Waves are what are called traveling disturbances. So you add an energy at a disturbance. So you throw the rock in the pond, right? Um, and then a wave carries that energy through a medium. So in this case, that would be the water, right? And you can see the waves spreading out like that. So a wave moves through space, but one of the interesting things about a wave is that the material itself does not have any net movement. In other words, as this wave moves from here out here, the water from here is staying there, and the water from here is staying there, and the water from there is staying there. Okay, so you have movement and oscillation, but you don't have any movement in the direction of the wave. So you can see that with our duck here. You know, the duck as it sits in the wave is going to be going up and down as the wave travels from, say, right to left here. But it's actually not going to be moving off to the right. Even as the energy from the wave moves to the right, the material and the medium stay there. And you can see that here too. So green is at t equals 0, right? This wave is moving off to the right, so the velocity of the wave is to the right. And as you would expect, you know, a moment later at delta t, it's going to have moved a certain direction, a certain length off to the right here, so delta x. But what's happening to the actual material? Well, imagine this is a string being shaken, right, and producing that wave. Basically, you're going to see this piece of material go in that direction, this piece of material is going to go in that direction, and that piece is going to go in that direction. So the material itself is going to be oscillating up and down, but the wave and the energy of the wave are going to be moving to the right. So that's one of the sort of interesting things about waves. So the fact that waves have that similarity with oscillation, that individual points are going to be oscillating, means we can use some of the same vocabulary that we used with oscillations, like period. How long does it take for the wave to go one full oscillation, right, up and down? Frequency, which is how many times per second, say, a wave peak passes a given point. And amplitude, so how far is it going up and down here? So x is generally considered the length from the midpoint to the maximum displacement there. But because it's moving in the rightward direction, we have a couple of other properties that are important. One of those is wavelength, right? So that's a peak-to-peak measurement, or a trough-to-trough measurement. It's the same thing, but it's that distance between two peaks in the wave. And then we have a speed of propagation, and that means basically how fast is that, you know, a given peak moving from left to right, the speed of the wave. Now we can think about that using some of our terms, right? So we have a wavelength. So speed is always distance over time, right? So our distance here is our wavelength, and the time traveled is t. And so we can find our speed of propagation as the wavelength over time. And then if we replace time by 1 over, or I'm sorry, t by 1 over f, that is the period, by 1 over frequency, we get this term here. And if you think about this term, obviously it's also in units distance over time, but what you're measuring here is basically how many waves per second go by, right, multiplied by how long the wave is, okay? And that's going to tell you how fast that wave is moving. Speed of propagation is interesting because it's determined almost solely by the medium of transmission. So how fast that wave is moving depends not on how hard you're shaking, you know, your string in tension. It doesn't matter how frequently you do it, right? How frequently you oscillate it, and the wave is going to move from left to right here at the same speed. And that's going to have to do with tension with the string, tension, and the density of the string. And so it depends on what we call rigidity, basically how
tightly together the molecules are packed, and density, low density, is going to move more quickly because there's less mass to accelerate. So if you look at a plot like this one over here, or a chart of different mediums, you're going to see a wide range in this case, the speed of sound in different materials. So in air, it's about 330 meters per second. The speed of sound through a rigid metal is 20 times as fast, essentially. So it makes a huge difference. And something less rigid, like rubber, is going to have a slower speed of sound. So if we know that the speed of propagation is constant in a given medium, like for instance air at environmental conditions, 20 degrees Celsius or whatever, then we know that frequency and wavelength are going to vary inversely, right? Because if we on the previous slide, we saw that speed of propagation is equal to frequency times wavelength. If we make this a constant, right, if we say the speed of propagation stays the same for all waves, then these two things are going to vary inversely. What that means is that a high frequency wave in air is going to have a small wavelength, and a low frequency wave is going to have a larger wavelength. When we think about different kinds of waves, there are two main categories of waves. One is called a transverse wave. In this, a transverse wave, the disturbance or the displacement is perpendicular to the direction of the wave. So here the slinky's moving up and down while the wave is moving from left to right. And then we also have a longitudinal wave, and this is what happens when we have sound. Is you get a compression here, and that compression travels from left to right. But that means that the displacement is also in the left or right direction. So here the displacement and velocity are perpendicular. Here displacement and velocity are parallel.